games. And we're going to study these games not as external artifacts, but as semantic constructions in their own right. So the idea is going to be we're going to embody this deception, this limited access to information about the structure controlled by some resource parameter by a comonad. And so for each value, for each type of game G, and each value of the resource parameter will describe a corresponding comonad. So we get an indexed family of comonads for each type of game. And this indexing will turn out to play an interesting role because of its connection with resources of some kind. So, well, you guys don't need this to be spelled out. It means that for each structure, applying this comonadic construction gives us another such structure. We have a co-unit, we have the co-extension. Here I'm giving the sort of comonad in Coakleys form. And then the idea is that duplicator strategies for the existential version of the games will be recovered as Coakleys morphisms for this comonad. And therefore, the notion of local approximation built into the game is internalized into the category of sigma structures and homomorphisms. So then, and what this leads to in the first instance, which is what I'm going to present, is comonadic and co-algebraic characterizations of a number of central concepts in finite model theory and combinatorics. So we are going to be able to reach into some quite important combinatorial parameters, as well as this issue of syntax-free characterizations. So let's start with the Ehrenfeucht. So there are going to be three types of game which are widely studied, and for each of those we will have a comonad. A complete picture of what the underlying story at the maximum level of abstraction is still in progress. But let's look at this first example, the Ehrenfeucht-Freysse comonad. So we're given a structure, and the universe of the new structure we build, so we call this E sub k, and this is where we play up to k rounds, is simply going to be the non-empty sequences of length up to k. And the co-unit map will send a sequence to its last element. Now, as it stands, this would just look like the list comonad. And as, so I guess everyone is familiar with lists over set as a monad, and it's pretty well known that if you take non-empty lists, they give you a comonad over sets. But here we're working at the level of these relational structures. So the interesting question is, when we take these lists, how do we lift the relations on the original structure to this new structure? So here's how we do it for a binary relation. We're going to define two sequences to be in the corresponding relation in E sub k of A, if first they have to be localized to be happening along the same play. So therefore, one has to be a prefix of the other. They have to be relevant to the same play of the game. And then so we can think of a sequence as really the last element in the context of the previous history of the play. So we say that the two sequences are in the relation if their last element, firstly, they have to be along the same play, so they have to be, one has to be a prefix of the other, and secondly, the last elements have to be in the original relation on the structure A that we started off with. And if you think about it, this is limiting the instances of the relation that we can have in this E sub k of A, so we just get a certain limited amount of access to the structure, and this is what will build in the model theoretic deception. And given a homomorphism, we define the coextension to simply give us the, so in, as a functional programmer would say, we get the list of heads, or the list of tails, sorry, the list of prefixes of the sequence. So we think of successive, so we take, formally we have a list and we look at the response to the first element, and that becomes the first element of our output. our response to the first two elements, and that becomes the second element, and so forth. And this is sort of the Coakleys presentation of a comonad, and it's easily verified to yield a comonad here. So intuitively, an element of the universe represents a play. A Coakleys morphism represents a duplicator strategy in this existential game with k rounds. Spoiler plays only in A, and the response to a list of I elements represents duplicator's response to the ith move by spoiler. And the winning condition is that after k rounds have been played, the induced relation is a partial homomorphism. So a first sort of check that we're doing the right thing. It's equivalent to have a homomorphism of this kind to duplicator having a winning strategy for the existential version of this Ehrenfreund for Issei game, and also to the preservation of existential positive sentences. Existential positive sentences are obviously less expressive than the full first-order logic, but they're actually very widely used. For example, conjunctive queries in databases and in constraint satisfaction. Okay, still, so this is, as it were, so a famous sort of piece of terminology about these kind of games is back and forth equivalences. Remember, spoiler could choose either to play in A and then we'd have to respond in B, that's the fourth, or he could choose to play in B and then we have to respond in A, that's the back. The prototype of all these arguments is Cantor's proof that there's a unique dense countable order, linear order. Isomorphic to the rationals. Although actually he doesn't quite use a back and forth argument in his original proof of that. In any case, so the first question we should ask is, what I've shown you is only this asymmetric existential positive case, which is what seems to correspond naturally to having a morphism in the way that we saw here. So the deception is only on the input side, as it were. How do we deal with the full back and forth formalism? And in fact, this is quite easily done. There are various ways of doing it. I'm just going to show something that will be familiar to people who've seen bisimulation. But there's an interesting point here, because it's a sort of folkloric thing that all these games are of the same general kind, but exactly showing, and one often in particular hears that bisimulation, that Ehrenfreund for Issei and bisimulation are essentially the same kind of thing, but I'm not sure that I've seen something that shows that they're exactly instances of the same general scheme. And we can kind of do that in these terms here. So here's what I'm going to do. I'm going to define the set of winning positions in this Ehrenfreund for Issei game. And this is just a rephrasing of what we've already seen. It's going to be the set of all pairs of sequences between ek of A and ek of B, which just have this property that the corresponding relation they induce is a partial isomorphism. Okay. So then we define this back and forth equivalence between A and B to hold if and only if this relation is a bisimilarity. What do I mean by that? Well, here I'm using the covering relation that goes with prefixes. So what it means is a relation is covered by something else if I mean, in other words, it's a prefix and there's nothing that sits strictly in the middle. So concretely, in this case, it means that we've simply added one extra move on the end of this sequence. The reason for writing it like this is that it applies to more general situations. Anyway, so we get this, we can now write a condition that will be familiar to anyone who's seen bisimulation, which says that whenever I have, so this, it has to be stable under sort of responses to moves by spoilers. If I have something that is a winning position here, which I might have reached by playing duplicator playing against spoiler, then whenever spoiler can move by extending where we got to in structure A by one move, then I have a response here where I play one move in the other structure, which takes me back into the winning positions. And symmetrically, if spoiler plays in the structure B, by adding one move, I have a response that takes me back into the set of winning positions. And we can define it other ways as well, in terms of existence of a suitable kind of span, or in terms of we can complete those partial morphisms to Coakleys maps and have some kind of fixed point characterization. At any rate, what we have is that the following are equivalent, that this back and forth equivalence holds between two structures, and on the other hand, that there's a winning strategy for duplicator in this Ehrenfeucht-Freysse game between A and B.
I'm sorry, so in that long-ish definition of bisimilarity, the first part sounded like if spoiler plays an extra move, then duplicator
Yes.
play an extra move and continue to win.
Yes.
But the second one seems to say if duplicator plays a move and it's
No, because now we're thinking of the symmetric game. So spoiler gets to choose either to play in A and then duplicator responds in B, or to play in B and then spoiler responds in A.
So the second clause, it's spoiler.
It's still spoiler duplicator, but it's spoiler playing in B. And that's exactly the thing we're adding over and above what we just had from having a homomorphism that was asymmetric. Right. And we can do that more sort of, we can do that in terms of the existence of a span of suitable morphisms, but I didn't want to go into that. Okay, but this general scheme is very familiar from bisimulation, and we can sort of write it in this setting in this way. Okay, so let's look at logics. We have the fragment of first order logic of quantifier rank less than k. We have the existential positive fragment of that, and then we have an extension with counting quantifiers. So this plays an important role in finite model theory. It means it's a sort of extension into a sort of weak second order kind of notion, in effect, but it allows you to say there are at least n things that satisfy psi. And if we're interested in capturing richer classes, then this kind of thing comes up naturally. Now, I'm going to use the comonad to induce equivalences on structures without mentioning logic. That's the game we're playing, and then show how these match up to our logical equivalences. So I gave a definition here that used some somewhat specific structure of the situation that we have. Roughly speaking, we know that the relational structures are concrete over sets, and the observation is that this comonad takes us to being concrete over trees, and we can use that language to write this equivalence. But here are two completely generic equivalences, which you can, on structures that you can define whenever you have a comonad. One is just the pre-order collapse, and then you take the corresponding equivalence. And the other is isomorphism in the Coakleys category. These are completely general. And then this kind of first matchup between logical languages and the equivalences they induce, model theoretic deception, as it were, in its different flavors here, and equivalences arising from these comonads. So we get that the existential positive one is just induced by the two-way homomorphisms. So the asymmetric nature of it means that you're only preserving the existential quantifiers and not negation, which will anyway let you express universal ones. The back and forth equivalence gives us the full language, and then the isomorphism gives us the ability to count as measured by this language with counting quantifiers. And moreover, these are all indexed by this resource parameter. So this is nesting up to depth k, and this is the sort of corresponding index on the comonad. Okay, let's briefly look at Pebble games. They're similar but subtly different to Ehrenfeucht-Freysse games. So as we were saying, in this case, each of spoiler and duplicator has a fixed store of pebbles. sort of glass bead game or something. So spoiler moves by placing one pebble on an element of either A or B, and duplicator responds by placing their matching pebble on an element of the other structure. And spoiler wins if after each round the relation defined by the current positions of the pebbles is a partial isomorphism. So you can play as long as you like, but there's a fixed size window on the structure which slides over different parts of the structure as you move the pebbles into different positions. So this pebbling technique comes up in a lot of places, and in particular it plays a fundamental role in finite model theory. Whereas the K-round Ehrenfeucht-Freycinet game corresponds to bounding the quantifier rank, K-pebble games corresponds to bounding the number of variables which can be used in a formula. So if you think about it, you can reuse variables that you quantify. So you can actually use two variables to say that there exists a path of any given length just by nesting your variables and reusing them, which sounds a bit of a hacky idea, but it's quite a rich family of logics that we get in this way. So corresponding to this, we have a pebbling comonad. We sort of introduce Pebble indices. We now allow lists of arbitrary length. So a move is now a pair consisting of a Pebble index and an element of the universe. This is placing that pebble onto that element of the structure. Otherwise, things look very similar. We now have the question, how do we lift the relations to this comonad structure? So again, let's take the binary case, and we see that again, we're only going to relate things if they occur along a single play. And again, they're going to be related if the last elements of the sequences are related, but the pebbling constraint on our resources comes into play in this clause here. If, say, the one sequence is that they have to be related, if you look at the shorter one, so the last move there is sitting there with some pebble, so the point is we're only going to relate it if that's still the current use of that pebble index by the time we get up to the later one. So that pebble index on the last move here must not appear in the suffix that we get by going up from S to T. So that's the way that gets defined, and then we see essentially the same way of defining the Coakleys coextension. By the way, this is, so it looks like much of a muchness, but it has some significantly different properties. It's clear that the previous one, which just took lists of bounded length, will be finite if the structure we started off with was finite. Whereas here we're allowing sequences of arbitrary length, so it's going to be infinite even if the original structure was finite. We actually prove that this is essential if we want to have the properties that we require. And this relates to the fact that if you look at that logical equivalence, at all finite resource levels, the elementary one where you bound quantifier rank is an equivalence of finite index over finite structures, and that's no longer true with this fixed variable fragment. So again, we have three languages indexed by a resource parameter. This is now the k-variable fragment of first-order logic, its existential positive version, and its extension with counting quantifiers. Again, there are two completely generically defined equivalences, the pre-order collapse equivalence and isomorphism in the Coakleys category, and we can instantiate the same bisimilarity scheme that we saw before just by varying the notion of winning position to be what I said it was, that you take the current positions of the pebbles, and if that determines a partial isomorphism. And we get the same kind of result in this case. There are some technical issues that come in about which structures, but for the cases of interest, we get a correspondence between these equivalences defined in terms of the comonad and the logical equivalences. Okay, so let me briefly show you the third of these, which relates to something very well studied in modal logic and concurrency, and then we can finish up by looking at some connections with combinatorial parameters. So in the modal case, what is modal logic about? Well, modal logic at the propositional level, classic idea is you can translate it into a certain fragment of first order logic, and that point of view has been very fruitful. So the idea is you talk about possible worlds, and the modalities say true in every possible world, true in some possible world. So in terms of our sort of setting, we're talking about relational structures with a vocabulary that contains symbols of arity at most 2. So you can think of the binary symbols as your sort of transitions or access relations that move you from one world or state to another. So it's really quite close to automata theory. So you can think of the binary relations as labeled transitions, so it's widely studied in computer science. The unary ones are simply properties that can hold a state. And one interesting point is that modal logic localizes, it's a sort of local semantics by comparison with full first order logic. Instead of being able to roam at will over the structure, it forces you to, I mean, you're at a particular world, and then you're at the worlds you can reach by following these transitions. And the natural way of reflecting this is to use the category of pointed relational structures. A model theorist would say we expand our signature with an extra constant, but it's useful. I mean, we like pointed categories and the like. So we can define a modal comonad, which corresponds to unraveling the structure A starting from the given element of its universe up to a given depth. Again, that's what this resource parameter is doing. And the universe will consist now, again, of sequences. So again, we're going to end up with a tree structure of some kind. There's the distinguished element is going to be the unit sequence of the thing we start off from. And then we're going to look at sequences we can get by starting at this chosen element, taking some transition to another element, some transition to another element, and ending up somewhere where we're allowed to take no more than k steps, starting from the root element that we began with. So one point is that the very universe here is already building in some information about the relations that held in the original structure. And we can get a correspondence now with simulation, which is the asymmetric version of bisimulation, which is proved to be one of the most important equivalence notions used in computer science. We can do the same, we can instantiate our same scheme for back and forth equivalences by choosing the appropriate set of winning conditions. In this case, if I have two sequences they both have to start at the same place. They both have to follow the same transitions. And the additional condition to be a winning position is that they have to satisfy, each of the corresponding pairs of states have to satisfy the same state predicates, the same unary relations. If we instantiate our scheme there and we still have this idea of a sort of a covering relation, a one-step move, and we instantiate the bisimulation notion that we gave before, then we get something that characterizes this bisimulation approximant bounded by the depth that you explore the structure to. And well, there's less familiar is what we do in the sort of counting case, but actually this has also been studied. There's a notion of graded modalities, where you say that you satisfy a formula possibly n phi if there are at least n possible worlds which you can reach from the given state which satisfy phi. So this has been studied and actually related to something studied in concurrency known as resource bisimulation, and everything matches up in the same way. Okay, so certainly this first round shows that we can capture these actually quite a diverse set of forms of model theoretic deception in a syntax-free way using these quite simple comonads. The second part is one of those nice cases where you get a bit more than you were originally looking for, explicitly at least. And that is that we have comonads. We know that comonads have coalgebras. What are they telling us? Well, a very nice feature turns out to be that they let us capture some crucial combinatorial parameters of structures using the indexed comonadic structure. Now, there's a nice conceptual point here. As we've sort of been emphasizing, we think of these morphisms as so the comonad builds in this limited access to the structure. So a Coakleys morphism only has to respect the k-local structure, which is where this model theoretic deception comes in. The lower the value of k, the fewer resources we have, the less information is available to spoiler, and the easier it is for duplicator to have a winning strategy. Or equivalently, the easier it is to have a morphism from A to B in the Coakleys category. So the duplicator can sort of fool the spoiler into saying there is a homomorphism because the spoiler can only see this limited window onto the structure. But now we can ask, what about morphisms where the comonad goes on the codomain? Restricting access to B makes it harder for duplicator to win the homomorphism game. Well, of course, what we then start thinking of is coalgebras. So what we're saying is we should only expect a coalgebra structure to exist when at level k, when the k local information on A is sufficient to determine the structure on A. And this indexing lets us open up a new kind of question for coalgebras, which we can sort of recognize may have something to do with combinatorics, which is very much about extremal values of various quantities. What's the least number of colors I need to color a graph, and so on and so forth. So given a structure, we can ask what's the least value of k such that a CK coalgebra exists on A. Okay, that makes sense. And we can call that the coalgebra number of A. So here's the result. So how many people have heard of tree width? Yeah, so tree width, for those who haven't heard of it, is a very pervasive parameter. I mean, originally, well, actually they weren't, so it became very well established in graph theory through the Robertson-Seymour work, and is now a major parameter used in parameterized complexity and combinatorics, algorithmics, and a lot of connections between logic and algorithmics. So it shows how tree-like a graph or more general structure is. Another important parameter is tree depth. And then, so what we find is that the coalgebra number of a structure exactly corresponds to the tree width of the structure, and for the case of the pebbling comonad, and for the case of the Ehrenfeucht-Fréissé comonad, the coalgebra number corresponds precisely to the tree depth, which is also found in Rossmann's proof of the homomorphism preservation theorem. And the main idea behind these results is that coalgebras on A are in bijective correspondence with decompositions of A of the appropriate form. So in a sense, then, we can say tree width becomes visibly a structure, in that to say that a structure has tree width k can be given by saying we have a coalgebra map to that value of the comonad. So then it becomes something we could build into a constructive proof of one of the various results that result in algorithms. So, yeah, I'll give the exact result shortly. In fact, there's a convention with tree width that means there's a difference of 1. But yes, I mean, other modulo a -1, it means the same. Yeah. Okay, so let me just, I think there's time to go through this. So I'm going to formalize it like this. I'll talk about forests and trees. So a forest is just a poset where the set of predecessors of each element is a finite chain. Graphs, I'll write the adjacency relation in graphs like this. And the forest cover for a graph is a forest which contains the set of vertices, and such that whenever two vertices are adjacent, then they're comparable in the ordering. So this means either v is less than or equal to v prime or vice versa. So the tree depth is defined to be the minimum height of a forest which covers G. So we're trying, so when things are sort of related, they all have to appear along a branch, and we're trying to squash down the tree so that we have branches that are no longer than they need to be. That's the way you should think of it. Now we can lift this from graphs, where it's originally defined, to structures, general relational structures. This is a standard trick in finite model theory using the Geifman graph of the structure. So the Geifman graph on the universe just defines two elements to be adjacent if they both occur in some tuple in some instance of one of the relations. They're both mentioned together and they're both related by something in this sense. So then, and we just transfer tree depth to structures in that way. So the result is that there's a bijective correspondence between forest covers of a given height, actually that should be less than or equal to, and coalgebras to the corresponding parameter, from which it immediately follows that the coalgebra number and the tree depth are the same. That's just an equality. Just to sort of see that, if we interpret the general, as we know, completely general coalgebra axioms in our particular case of the Ehrenfeuer-Isse comonad, where you have these lists, well, suppose we had a coalgebra. How does it look? It sends each element, A, to some sequence, A1 to AI. So the first axiom is telling us that AI has to be sent to this sequence. Sorry, each AJ, where J is sitting somewhere here, has to be sent to a prefix of this sequence. If you hash out the equation, that's what it's saying. And the second one is just saying that the last element here has to be equal to A itself. So altogether, that's saying that if there is a coalgebra, it's sending, it's injectively mapping the elements of the universe into a sub-forest of the forest of sequences, non-empty sequences. And we can then transfer that partial order to the universe itself, and we get a forest cover. And once we know that we can match heights of forest covers in this way, then we're immediately going to get that the coalgebra number coincides with the tree depth. And tree width is interesting. This is an enormously well-studied notion, slightly more complicated, so let's just take a moment to look at it. A tree is a forest with the least element, the root. There's a unique path between any two elements. You go up to their sort of common ancestor and then down again. And then a tree decomposition, this is the classic definition a la Robertson-Seymour, is a tree together with a labeling function which labels each node of the tree with a set of vertices of the graph such that every vertex has to show up in some label set. If two vertices are adjacent, they have to occur in the same label set somewhere. And if a vertex is in two label sets, it has to occur in every label set along the unique path connecting those two nodes of the tree. And then the width of a tree decomposition is given by the maximum size of label sets minus 1, which is a convention that allows trees to have tree width 1. That's just a convention. And then we define the tree width to be the minimum width as we range over tree decompositions of the graph. So that's the notion. So as we've said, it plays a fundamental role. So we're now going to give an alternative formulation of tree width, which will bridge us over to the co-algebraic characterization, which I think is actually quite interesting. It relates tree width and tree depth and shows how pebbling arises naturally in connection with tree width. So remember the forest covers, just a forest, and then if two vertices are adjacent, they have to be related in this forest ordering. One has to be an ancestor of another. So we now have a k-pebble forest cover is a forest cover together with a pebbling function such that whenever two vertices, and here we're taking it just to be an order on the vertices of the graph itself, together with a pebbling function such that if two things are adjacent with one, therefore, since it's a cover less than or equal to the other, then going from one up to the other, the pebbling value doesn't coincide. So this should be reminiscent of our definition, the way we lifted relations in the pebbling comonad. And now the result is that the following are equivalent. You have a tree decomposition of width less than k, and you have a k-pebble forest cover, from which you immediately get that, so that is purely at the level of the combinatorial definitions itself. It's showing that, I mean, if you think about it, this looks very different to the tree decomposition definition that we saw here. Here you had a tree standing over there labeling with sets of vertices from the graph, and now we're just ordering the vertices of the graph and pebbling them in this fashion. So it's not entirely obvious that they coincide in this way. It needs a bit of a proof. Once we have this k-pebble forest cover, though, we can do very much a similar argument to what we saw with the tree depth to show that co-algebras correspond to k-pebble forest covers of the Geifman graph of the structure. And then the result we get is this match up to this convention about subtracting 1. Yep. Okay, so I think this gives a hint that by introducing indexed and graded structures on monads and comonads, we can start to get access to some of the typical definitions and modes of thought of combinatorics and algorithmics. And I think my feeling is that there's quite a lot of scope for further connections of that kind. Of course, these monads are not just discretely indexed, they're certainly a functor on the poset of positive integers into the category of comonads, and so that means that you get monad morphisms that include k-level Ehrenfeucht-Fréissé into, say, k+1 level Ehrenfeucht-Fréissé, because playing up to k rounds is a special case of playing up to k+1 rounds. And in fact, we can even see that these comonads are trivially graded. So graded monads and comonads have begun to play a role in functional programming and categorical methods in computer science. And it will be interesting to see if there are more interesting graded structures. So a comonad is a comonoid in the endofunctor category. And this generalizes to the idea of a graded comonad, which is an oplax monoidal functor from a monoid or maybe a monoidal poset or something into this endofunctor category. So that's the general definition. So the question is, in this sort of setting, whether they're more interesting graded structures than just indexing by positive integers, which would arise naturally in considering richer settings. Obviously, we've been looking at finite levels, but because we have these inclusion morphisms, we can take colimits and obtain comonad, say, at the omega level, which would correspond, say, in the bisimulation case to unfolding of a Kripke structure to all finite levels, and this will correspond to the usual bisimulation approximate up to omega levels, which is the full bisimulation on image finite structures. And we can, of course, continue beyond omega should we have a wish to do so. Okay, so it's clear that these all have a striking unity. I'm sort of still haven't quite got a clear picture of a sort of more general construction of which all of these things are instances, but quite a lot of, I mean, and as we saw with the bisimulation, quite a lot of common structure is apparent. But there are also interesting differences. As we saw, you always get a finite structure from a finite one with the aerofoil for Issei case, but you get necessarily an infinite structure in the Pebbling case. So we need to understand better what makes these constructions work and what the full scope of these ideas are. There are some natural extensions to other kinds of logic, many of them involving reaching into second order logic, which plays an important role in the logic and algorithmic world. And coming back to the remarks I was making at the beginning, what would really be good is to push things to the point where one can, using these kind of means, really get to some of the major theorems in the area, hopefully, of course, even extend and improve them. So let me just mention a couple of things, I think them which may be within reach. There's a result known as Courcell's theorem, which is a sort of prototype of a so-called algorithmic meta-theorem, which says that for another logical language, monadic second-order logic, any property of graphs you can describe leads to a linear time algorithm on graphs of a bounded tree width. So in principle, from the description, you can get to a linear time algorithm, admittedly with some unpleasant constants, but I mean, that's been improved in various ways. But it's one of the signature results in the field. If we're thinking of bounded tree width as witnessed by a coalgebra in the way that we've seen, and then combining this with some other ideas that I haven't discussed here, one could imagine a categorical proof of this result, and perhaps even then using a suitable type theory sort of automatic extraction of the algorithm. And I think that would be something of a success story in pushing categorical methods into new territories in computer science. And similarly, guarded logics are substantial extensions of modal logic which are decidable, and the kind of way that works using the tree model property, which is very much related to this comonadic analysis, also seems promising for something that we could study using these methods. Okay, so I'll finish there.
There's time for some questions. Any questions? So if we think a bit further than cryptoframes and the graded model logic, so think about 4+4 quantum. We know that bisimilarity can characterize a relation between the quantums and equivalent. So I mean, I wonder if this. I mean, first of all, do you see your work going?
Coalgebraic modal logic.
Yes, yes. So we know that there is a kind of, well, we can have generic and similar style theorems and call it like modal logic, but
yes.
Not as finite theory. We know that there is an expressive modal logic.
Yeah. Yes, I agree. I agree that's natural. So I guess that obviously I've been focusing more on the sort of a traditional model theory, finite model theory I don't know if there, how much of a connection has been made between coalgebraic structures and first order or second order logics. I guess there's been some.
So there are algebraic characterization theorems from then on this time.
Right. Yes.
And
yes.
also use the Greitman graph, so this work by Patterson.
Yeah, I should definitely look at that. Yes, as a monadic second order logic for coalgebraic structures.
There's also a algebraic version of the Janin-Walukiewicz theorem that says that the algebraic mean hypothesis is that isolation and variant fractal.
Right. Yes. Yes. Yeah. No, I agree. That would be a natural and good thing.
Yeah. So I was wondering about the connection between relation lifting. I mean, bisimilarity defining terms of relation lifting for the function, the qualitative function, and your notion of relation lifting. It seems like there's some. I think there's some connection. I can't really see exactly.
That's interesting. Yes. Yeah, it's definitely. Maybe we should discuss that. Yes, but that would be interesting. Yes, I don't see that immediately, but yeah, it would be. I mean, what about the guarded logics? Because I mean, the coalgebraic modal logics generalize propositional modal logic essentially. Guarded logics, you get this quite non-trivial extension to arbitrary relational vocabularies that has a lot of the. Does that sort of play into the, does that connect with? Because at the moment, that's the thing that seems most, I mean, a sort of immediate challenge is to be able to come with that.
But your part was indeed best was saying something about how modal logic sits inside the guarded fragment, of course.
Yes.
Whereas the characterization theorems, I mean, they're certainly translating to the guarded fragment, but yeah. I'm not sure to what extent the qualified characterization theorems really use that somehow.
Okay, well, we should maybe, but thanks for the comments. Yeah.
So there's been previous work on sort of categorical approaches to combinatorics using Joyel's theory of species.
Yes.
Do you know of any connections with that?
No.
Okay.
I don't see it. It would be nice, of course, but I mean that's mainly to do with sort of enumerative combinatorics. This is clearly related to the sort of actually quite extensive now approach to graph theory using homomorphisms, and I don't see it. So I think there may be sort of getting at different parts of combinatorics. What I find is nice here is that this idea of the sort of extremal value of some parameter is kind of comes up in a natural way, and you can then say something precise that does relate.
Are branching quantifiers Hindecker quantifiers?
Yeah, so Hindecker have this independence-friendly logic, but which is a generalization of branching quantifiers. But a more user-friendly version of independence-friendly logic is, I think, is the dependence logic of Yoko Vanneman. So that's what I've got there. But that is essentially the same thing as the Hindecker.
So there are applications to natural language of
yes.
and so official.
Yeah, that's right. So it would be nice to bring that in the scope of this. These are all things that extend in one way or another into second order logic. And it would be nice to capture some of those.
And they are related to puzzles like all men like two cars. The branches quantifiers help you solve the two different readings of that kind of example.
Yes.
That
no, I mean, yes, and it might. I mean, it might be informative. I mean, there might because we have. Okay, let me make this comment. Because we have a sort of handle on resources somehow here, there might be some way of grading that so that you could relate that to the sort of difficulty of different kinds of nesting constructions that you would get by translation from natural language. By the way, I'm very disappointed you didn't mention anything about donkey sentences in your talk.
Too difficult. But we could, if you talk about branching quantifiers in the setting, then you can also very easily talk about donkey quantifiers. Yeah, but we don't know how to do them in compositional distribution semantics. Yeah.
So you choose,
Every farmer who has a donkey beats it.
Anyway, yeah. Well, that's good, but yeah.
We have a room to discuss donkeys.
Yeah.
I don't know if this is in algebraic geometry or things like that. Maybe we take projective resolution and things. And these are, people talk about projective dimension of a ring or something like that. So this is like with the sequence of k. Resolve this in k many projectors or something. Is that at all something that might fit in?
Well, I mean, I've sort of had the feeling that one can do this general sort of routine to different kinds of structures, not necessarily these kind of discrete relational structures. So I've been thinking about various sort of things one might be able to do with metric spaces and so on. I mean, obviously, what you're describing is more sophisticated, but yes, I mean, it would be great if one could do something similar there. And yeah, because it sounds like, I mean, yeah, so you've got a sort of, it's losing some information, but you're getting this kind of grading that gives you...
Free resolution.
Yes.
I guess free is a monad.
Yeah.
A free group or whatever.
Monad or comonad?
Well, yeah. Maybe injective.
Yeah. Well, okay, no, that's...
You just keep take an object and keep it with a monad or a comonad. Yeah.
Yes.
And then you say the kth dimension,
I see. Because here we're not exactly iterating the comonad. We're sort of, we have a sort of index along which we can define a... yeah. Well, I mean, it would be great to have examples of a sort of more general mathematical character which arose naturally. So, yeah. Did you have a...
Okay, so just before we thank Samson again, I'll just say there's a coffee break now until, say, 1:30, and then afterwards we've got discussions. The discussions are software for ACT, including a demo of the globular software. But one here, richer syntax, that's a kind of extension of what we were talking about with the linguists earlier, and actually donkey sentences, if you are interested in it, could go into that. And then in the organisers room, there's a discussion about, which is going to happen each day, about all the previous days plus that one. No, so today is causality and AI information. Tomorrow we'll add on each. Okay, but for now, sorry.
Just to give a bit more information about the first session. So software for ACT means both Jamie and possibly Alex and Yella will give an overview of existing software like Globular and Quantumatic, and also stuff in development. And then, so that'll be the first half hour, and then after that it'll be free for people to sort of create some sort of wish list of where this should go and what software